they're okay. I shouldn't have said that after I clicked record. Oh, well. All right, so now I'm going to integrate this just term by term using our power rule that we 100% have to know. So this would be, let's see, 1/3 x cubed. Bump that up to squared and divide. So 3x squared plus 9x. And as some of you found out when you got your quiz back, we still have to put plus c. And it's very easy to forget. Now that we've done definite integrals where you don't need it, it's easy to forget to put it. But you always need to put plus c, especially if you're not doing a definite integral. I haven't taught you anything yet. Taught you nothing new. But now is kind of the new stuff. So let's say I want to integrate x plus 3 to the 4th power. Okay, well, technically, you could do what we just did in example 1. You could write x plus 3 4 times, multiply it all out, which would take a little bit of time, and then integrate term by term. Like, you do have that option. But I'm going to show you guys a new way, because if this was x plus 3 to the 40th, then you can't do that. I guess you could, but not in the allotted time of what it would take. I don't even know how long it would take to do x plus 3 to the 40th, like expand it out. I bet you guys couldn't do it in a whole day. I bet not. And get it correct. I bet not. Anyway, that's besides the point. In my mind, I was like, should I do this? Should I try it? Not like right now, but just in my free time. But I'd rather not. Okay. So if I want to do x plus 3 to the 4th, here's u substitution. All right. This is the big integration technique that we use. And this is going to come up a lot in our next chapter as well. So this is a big idea. So here is what happens. I want to get anything that looks like an x to become a u instead. That's big idea number 1. Okay, I'm going to explain how we go about doing that. But pretty much any inside function, like if I go back up to this chain rule problem, I circled the inside function. I circled x squared plus 5. That's my inside function. Well, Caitlin Decker, what looks to be the inside function on this integral? X plus 3. Okay, so what I'm going to do is any inside function, I'm going to define that as u. So here's kind of my process of work. I'm going to let u equal whatever my inside function is. So in this case, x plus 3. U is x plus 3. Okay. So if I think about what I just did, I have basically now this is u to the 4th power. This is u to the 4th power. And that's good because I could just do the power rule. But I can't just yet because I would basically be having a u expression, but integrating it with respect to x. And that's bad news bears. Those conflict. So what we also need to get rid of is this dx somehow. And we need this dx to become a du somehow. And here's how we make that happen. So now I am going to differentiate both sides of this expression. I take the derivative of both sides with respect to x. So what this looks like is, okay, if I take the derivative of u with respect to x, I write du dx equals, and then the derivative of the right side is just 1. Now, once you get to this step, the reason this notation is really nice in calculus is because it behaves like a fraction. You know, I've talked about separate the variables, separate the variables, separate the variables. That's basically what we're going to do right now. I'm going to take that dx and move it to the other side of the equal sign. So what I just said is I want to get anything that looks like an x, that has an x, and get it all in terms of u's. That includes the dx as well. Now I picked the most basic, easiest problem that I could to start with. I want you guys to understand this because this is not always going to turn out where dx is the same as du and I can just straight up replace it. That's not always going to happen. This problem was designed just for you guys to see the steps very quickly. So once I get here, okay, I'm trying to replace this expression. I did, that's u. And then I'm also trying to replace dx. And I just figured out I can replace dx with du instead. So my new integral is going to look like this. It's going to be, oh, there's Sydney. Instead of writing x plus 3 to the fourth, it's going to be u to the fourth instead. And instead of integrating with respect to x, we replace dx with du. Once you get here, now it's just your normal integration, your power rule. So I'm going to bump this up to 5 and divide by it. So it'd be like 1/5 u to the fifth plus c. And then the very last step is do your back replacement. Take what u was and replace it back with what u was to begin with. So instead of putting a u here, I'm going to replace it with x plus 3. Now, there's a couple of things I need to point out, because if it was me sitting in your chairs and I just saw this very first one and I look at the problem and I look at the answer, I'd be like, wait a second, why at the very beginning didn't we just bump this up to 5 and then divide by 5? We get to that same exact answer. This problem was designed as basic as I possibly could, where if I made that 2x plus 3 in the parentheses, it wouldn't work out that way. So this problem is very coincidental. You can't just bump that up to a 5 and then divide by it. But that is our process. We define u, we take its derivative, we replace, and then we integrate. This procedure takes some practice, okay? So let's look at the next one, show you another one. So example 3, I want to integrate 3m squared times the square root of 4 plus m cubed. And as soon as you guys see something that looks really messy, in your mind think, okay, I probably got to do u substitution. And the first thing I'm going to look for is any inside, like nested function, any inside function. Mr. Cologne, what looks like to be like an inside function?
4 plus m cubed.
4 plus m cubed. So I'm going to take the entire inside function, 4 plus m cubed, this whole thing right here. Not just the m cubed part. I get a lot of students that'll just have u be m cubed. You want it to be whatever the entire inside function is, you want u to be that. So off to the side, I'm going to have u be 4 plus m cubed. Okay, so think about what that does for us. That gives us the square root of u, or in other words, u to the 1/2 power. That's pretty good. But we also have to get rid of the 3m squared and the dm. Like we need all that to turn into u's as well. Well, as soon as you define u, your next step is always to take the derivative of this line. Now on this one, we're taking the derivative of u, but this time it's with respect to m. So on the left side, I would write du dm equals, and then I'm going to differentiate the right side. So 3m squared. Remember the 4 goes away. Then I'm going to take that denominator and move it over to the other side of the equal sign. In fact, once you do enough of these, in all honesty, I don't ever write this line in my work. It's not required. What's always going to happen is like you're going to differentiate the right side and get d whatever that letter is. I show that, especially for the first few I do, to show you where that dm or dx comes from. But once you do enough of these, a lot of you will just go straight from this line to this line here. And then I try to think, what am I trying to replace? I need all the m's to turn into u's instead. Well, okay, I have the square root of 4 plus m cubed, but now instead it's the square root of u, so that's good. And then I also needed to replace 3m squared dm. 3m squared dm. Well, look at what just happened. 3m squared dm, that thing I'm trying to get rid of, all of that is just du instead. Like I can replace 3m squared dm with du. All that stuff goes away and it is du instead. So now I have the integral. Well, this would be the square root of u. So instead, I'm going to write u to the 1/2, because any radicals, we just turn into exponents. And instead of writing 3m squared dm, all that other stuff, we just found out all that stuff equals du. Once I do all my replacing, now I integrate like normal. Now I do my power rule. All the hard stuff is done. Now I just integrate this. So this, I would bump 1/2 up to 3/2 and divide by 3/2. So 2/3. Plus c. And then I take what u was and plug it back in. That is u substitution. What do you guys think? These two are pretty much as basic as I can make them. Not to say they get a lot harder, but there's like one extra thing that could happen. It's going to happen in the next one that I'll show you guys. But I want to make sure I stop and get any questions answered on at least these two basic ones. I say basic, but I realize you guys learning this stuff for the first time. I remember learning this and I didn't like it. That was 18 years ago, but I remember learning it. You guys ready for the, yeah.
So when you got from the u to the du on the left side,
Mhm.
and then you got what was like left in the original equation,
Mhm.
that just left, did it happen this time, or did it be like that every time?
I will not be like that every time. So his question is, well, did it just so happen that the other stuff turned out to be du? That was not just luck, but because I made the problem that way. And you're going to see on the next one that that won't happen all the time. And we'll see what we got to do to deal with that. Okay. You guys ready for the next one? Are you ready? Graydon, are you ready? Are you still ready?
Oh, yeah.
All right. You haven't lost your mojo? Nice. Okay. We're going to skip the general notation here. I've gone over that. It never helps. All right. So I want to integrate the square root of 3n plus 1. So before you can do anything, though, you have to recognize when you need to do u substitution. Like that's the most important part. Kind of like when we learned chain rule for derivatives, you had to know when to do chain rule. It's not a hard rule to do, but a lot of people forget when to do it. As soon as you see a function inside of another function, you're going to have to do u substitution. So my innermost function is 3n plus 1. So I'm going to have u be 3n plus 1. And immediately, as soon as I define u, my next line is differentiate that. Now, if you're someone who you think you might forget to put, like in this case, the dm, or on the one up here, the dx, if you think you're going to forget that, then if it were me, I would write du over dn equals 3, and then move the dn over. Okay. But I'm at a point where now I just write du equals, and then I differentiate the right side, and I put d whatever letters over there. Like I just jump straight to that step. Now I want you to see what we have going on here. Okay, 3n plus 1, that's u, so that's u to the 1/2. That's good, I got that. But the other thing I need to replace is dn. The only other thing I have to get rid of is dn. That's it. Well, on the previous two, the thing on the right side turned out to be exactly the stuff that we needed to replace. Well, here we have an extra 3 over there. This is like the one other thing that could happen with u substitution. I'm trying to figure out what can I replace dn with. Well, okay, that means take this equation here and solve it for dn. Figure out what we can replace dn with. So I can divide both sides by 3. So I would basically have 1/3 du equals dn. So I have all my replacements. I'm going to show you what happens next. Okay, so I would have the integral of, well, this would become u to the 1/2. And then instead of putting dn, that's the same as 1/3 du. What I do, and this is me, but I wanted to show this so you guys could see like where stuff's coming from. But anytime you have this number in front of the du right here, which is going to happen a lot, this is probably most likely what's going to happen in the U substitution problem, where you have to divide by whatever that constant is, and you get a number in front of du. This is like the most likely problem you guys will encounter. What I do is I don't like to integrate with constants inside the integral. So I just pull the 1/3 out in front and then deal with it at the end. It's a nice little property. So when I'm doing these problems, I jump straight from this line to this line here. Like if ever I have a number in front of du, I just write that number in front of the integral. Because, and some people don't like that. I have a lot of students that don't like doing that, and they like taking all these steps. That's fine. I'm not against that. But I know some of you like shortcuts and stuff. So I just jump straight from here to here. And then I do what I did on the other ones. I'm going to actually integrate u to the 1/2. So let's see, this would be 1/3. And then that's going to be 2/3 u to the 3/2 plus c. So that's 2/9. Just multiply those fractions. So 2/9. And then replace what u is. U is 3n plus 1. So plug 3n plus 1 in where the u is. What you guys think? Yeah.
So when you take that 1/3 out, it doesn't multiply by the entire function?
It does. His question is this, and it's a good question. So he's saying you have this 1/3 in front of the integral. So his question is basically, shouldn't it be 1/3 and then times this thing? It is. So when you distribute the 1/3 here, you would get 2/9 u to the 3/2. But what's 1/3 times some arbitrary constant? It's just some other arbitrary constant. There's no point in putting 1/3 c. So it just kind of wraps that c in there. Yeah, that's a good question. What else? Other questions? Yeah.
Would we ever be given this like with a point to find c where the 1/3 would need to go like in parentheses?
That's a good question. It's possible. It's unlikely, but it's possible. So that's why I could just say no, it's not going to happen, but that'd be lying. Like it's possible, it's just rare.
Okay.
Yeah. All right. I want you guys to try example 5. Por favor. Have the work up there in case you're done or stuck and you want to see. These are ones that you just have to do on your own, because if you do it right, like 5 times in a row, then you have it down. But if you're missing it, there's usually like one reason why. And so it's just up to you guys to find like if there's an issue that you have with it. But you guys tell me. What do you think? Said you hate it? I know. All right. Have you try one more? Try this one. Try to integrate x squared times the cube root of x cubed minus 1. I triple dog dare you. Ready, triple dog. I have a few. Anybody ever do one of those DNA tests and find out they're related to anything cool? No? Okay. All right. Thought that would have been a cool storytelling moment. All right. There it is. Do we get it? You guys aren't getting it. What do you think, Justin?
I have a question.
Yeah.
So, an example, 3, why didn't you say 1/3 du equals m squared dm?
Because, so from this problem, we were trying to get rid of x squared dx here. But when I differentiate, I end up with 3x squared dx. So once I do my derivative, I then need to think, what am I trying to replace? So from this one, I'm trying to replace x squared dx. That means I have to get rid of this 3 and move it to the other side. But on example 3, I was trying to replace 3m squared dm. And it just so happened 3m squared dm, the thing I was trying to replace, showed up here. Like all this stuff was the stuff I was trying to get rid of. So I didn't want to move the 3 over.
Okay, thank you.
I don't think, I'm no psychic. That didn't sound confident.
No, it makes sense. I was just confused before.
And now it sounds like you're trying to act confident, so we just move along. Okay. All right. So use substitution. This is like our one integration strategy. It comes back up again, like I said, next chapter, because I don't know if I've told you guys this or not, but next chapter it's not the most fun because it's a lot of just rules. You guys are going to learn how to differentiate inverse trig functions. You're going to learn how to differentiate exponential functions like e to the x. You're going to work with log functions. So they call them transcendental functions. Up till now, all we've worked with are like polynomials and trig. We haven't done any exponential functions or inverse trig functions or log functions, and that's what next chapter is all about. It's not extremely difficult. It's just not fun. Everything else we've done is fun, but so, you know. Now, if you haven't thought everything we've done is fun, then you're in trouble next chapter. Anyway, but my point is, use substitution comes back again. Today, the only other thing to learn is how can we apply this with definite integration? It's the same process. It's just understanding that when we're doing a definite integral, our final answer still needs to be a number. Don't lose sight of that. If you're doing a definite integral, you still need to get an answer of like 6 or whatever. But I also kind of want to point out why use substitution has worked on all these. I don't know if you guys care at all, but I think it's important, especially for those of you moving on to math classes. Like, use substitution doesn't just work every time. The problems are designed for them to work. Like, for instance, if I made this right here be x cubed, there would be no way to integrate this problem. What's happening is, it just so happens the derivative of the inside function shows up as the outside function, like some form of it. Like the derivative of x cubed is like x squared, and x squared shows up on the outside. Or coming back over here, the derivative of 4 plus m cubed is some form of m squared, which shows up on the outside. That's what's happening on these problems. So I think that's important. If you look at number 7, same thing happens. Like the inside function, x squared plus 1, its derivative is 2x, emphasis on the x, which shows up on the outside. So these problems are designed to work, but that's how you can kind of hone in on when you're going to be doing it too. Okay, so to do a definite integral, it's the same process to start with. We are going to have u be our inside function. So I'm going to have u be x squared plus 1. And then just like on all the other ones, I'm going to differentiate both sides. So du equals 2x dx. I remember especially when I first started teaching this class, I would forget to put like the dx on the end all the time. And then I would actually kind of get stuck in my work when I'm trying to figure out what to replace. Make sure you guys put that dx. Normally it's x. Make sure you put that dx on the end. Once I get here, I always stop. And now I think about my substitutions, what I'm trying to replace. And Brooke, maybe this will help. So this right here is u. So now that's u cubed. And I'm also trying to replace the other stuff with x's. So x dx. I'm trying to get rid of x dx. And I look at my line right here, and I don't have x dx. I have 2x dx. That means I got to divide by 2. I got to move the 2 over. So this would be 1/2 du equals x dx. Steps 1 and 2 are generally pretty easy. You have u be the inner function, and you differentiate both sides. It's that next step, like just stopping and figuring out your substitutions, that is crucial. Okay, so now I have the integral. I'm gonna put the 1/2 out in front, and you'll find out if you like doing that or not. I have some students that will think they're going to remember to do it and then just don't remember to put that number out in front. Then I have u cubed, and x dx becomes my du. Now I want you to notice I didn't put my limits of integration here. This is like the big idea for definite integration. This is the wrinkle with definite integration. So initially, our limits of integration, 0 and 1, since all of this is with respect to x, these are technically x values. But now that I'm integrating all this stuff with u's, I need to change these x values to become u values instead. And the way I do that, I use this equation right here. This equation tells me how to change x values to u values. So like initially, if this x value is 0, so when x is 0, if I plug 0 into this equation, 0 squared plus 1, the corresponding u value is 1. So 1 would be my new lower limit. And then the upper limit is 1. So when x is 1, if I plug 1 into this equation, 1 squared plus 1 is 2. Now here's the nice thing. When you change those limits, once you change those to u values, you never have to look back to the x's. Like you never have to go back and plug anything in for u. Like now just do all your work moving forward with just u's. Don't change them back. I'll show you what I mean by that. So I have 1/2. I'm going to integrate u cubed. So 1/4 u to the 4th. From 1 to 2. Keeping in mind, guys, we're doing a definite integral now, so we don't need the plus c. Now I'm going to plug 2 in for u. Little tip, if you guys have a fraction here and then a fraction on the inside here, you can actually pull that 1/4 out. I said 1/4. You can pull that fraction out, multiply those together. Saves you a little bit of mental math. Basically, you're taking that 1/4 out and then just plugging the 2 into the u to the 4th and the 1 into the u to the 4th. If this is a free response question, I stop here. I don't mess with this stuff. I leave this answer. I've talked to you guys about that. I'm not joking when I say that. I would leave that answer and I'd move on. It's all numeric at this point. Once you get to an all numeric line, you're done. But for those of you that don't like that, this 2 to the 4th is 16 minus 1, so that's 15. So 15/8. Now your other option, let's say you don't want to change those to be u values. I will say 100% you have to know this process because a lot of times they'll do multiple choice problems. This is very common. They'll do multiple choice problems where this will be the problem. And then they'll have a bunch of things that look like this as the answer choices. And they'll say, which of these answer choices is equivalent to the problem? It's like you have to know how to change the limits of integration. Because what I'm about to show you next, you technically don't have to change the limits. Because let's say that you were like, well, when I integrate u cubed, I'm just going to put x squared plus 1 back in for u right here. Like here's your other option. You could have never changed those limits of integration and done this instead. If you plug the x squared plus 1 back in, then you could keep those original limits and now do the problem from here. You could plug 1 in for x and 0 in for x using those x values. And I have some students that they're like, well, I'll just always remember to plug the x expression back in and then never have to worry about changing the values. Like I said, they get creative with how they ask questions and they force you to know how to change those limits of integration. So it is a process you have to know. Last one. Try it out. And then we'll be done. Oh man, we have 30 minutes left. How'd that happen? What happened? I made a note to myself. These notes take like the whole class. That's Forewarn you, the numbers on this one kind of get grossly big. But if you know what 72 cubed is, then you'll be fine. I just didn't want you to think you were doing it wrong if you ended up getting like big stuff. Like everything's melting out there. That's good. I didn't want any of them done on the way home. There's the answer. You were close to the end. 72 cubed, by the way, is 373,248. You may know that. Nobody knew that? Peter, you didn't know that? Got any questions? You guys at home got any questions? This must be the easiest thing ever. I wouldn't have thought so. Anybody listening to me? Am I on mute? In person? A couple years ago, I had lost my voice. Like I couldn't speak at all, but I still taught a whole calculus lesson. I got on my computer and I typed what I wanted to say. So they had to like read everything. It actually worked out really well. It was the quietest that class had ever been. Yeah.
So you don't need to, at the end, you don't need to plug the u function, so like the x cubed plus 8 back into the.
If I'm doing a definite integral, I would not plug the x cubed plus 8 back in for you.
Okay.
It's not wrong. Like that's why I was showing two different ways you could do it. You could either change your limits and keep it all in terms of u's throughout the rest of the problem, or keep the original x's and plug your x stuff back in.
Okay.
You could do it either way. It is important, like I said, I said this on the last one, it is important to know if you're someone that you went back to the x values, that's fine. But like I said, on multiple choice questions, like this will be the answer. So we do have to know how they get those limits of integration. A lot of students will get tricked because they'll pick the option with 1/3 u squared du, but they'll pick the option that has the original limits that say -2 to 4 here, and that's not correct. So as long as you don't get tricked. Okay, my very last question, and then you guys at home can go. Brooke, I'm gonna ask you, so be ready. Are you ready?
Yeah.
Okay. What's the difference between these two things?
One is displacement and the other one is total distance traveled.
Do you know which one is which?
Isn't total distance the first one? Just kidding, the second one.
That was a funny joke. This is displacement. We talked about this last time, but it is an important topic. I just want to make sure I reminded you guys. This is total distance traveled. Okay. That was all. You guys at home are free to go. You have homework, but nothing Wednesday. I could have done something, but then I would just be doing something to do something, and that's not fair to you guys. So I just didn't. Oh, they're all gone. Oh no, Aiden's still there. Aiden, what's up, man?
What's up?
Hey, you having a good day?
Yeah, I'm all right.
Have you done anything fun today?
I gave my dog a bath.
Nice. Does he like it?
No, they hate it.
Oh, you gave multiple dogs baths.
Yep.
Well, that's cool. Playing video games?
No.
Had class all day?
Kind of, yeah.
What was your best class today?
Weights.
I can't fault the honesty, man. I appreciate it. All right, you're free to go. Wait, she's at home. It just hit me. What do you do when you're at home for weights? Are you supposed to though?
Supposed to warm up on camera, but no one does it, so.
Why?
This is awkward.
Do you do it with the camera off at least?
Sometimes, just depends. I mean, you're not on camera. Well, if I worked out already.
Well, don't you get in trouble if you're not on camera and you're supposed to be?
Not really.
Mm.
Sometimes they're like, no ceiling fans, but then everyone just keeps their ceiling fans.
What does that mean?
Like, we have our cameras just facing up, like,
Oh.
not on us.
Mm. You guys do that on purpose?
Well, yeah.
You guys are slick. Oh yeah, one lesson left. Area of trapezoids. Okay. Good day, good day.
How you work doing typing? I just camera's off. Yeah, you're doing great. It's a good job of work.
My wife just texted and said my son had a meltdown doing homework today. Well, that's not good. I'm glad I wasn't there though. Sucks for her. They're doing multiplication right now. Lattice method and box method and standard method.
I don't even know what lattice is.
Box method.
Wait, I thought lattice wasn't.
It's like you multiply like the one on the top and the side. and then
What's
like-
Lattice, I don't know. Well, I know it's like you have lines or something.
Yeah, I know what you mean. What about just the normal, like, carryover? Honestly, I don't even know how I multiply writing down.
I don't know.
Actually, yeah.
See, last year, his teacher, he's in advanced math. They started last year. And his teacher was really good because she taught the lattice method, but she also told them if they knew how to do standard, they could do it that way. So we taught him that way, and he did it that way every time and got them all right. This year, they have to know how to do multiple methods. Well, I don't disagree with the rectangle method because so if I said do 24 times 8, like in my brain, I do 160 plus 32.
Yeah, that's how I.
Right, that's not standard. Standard would be you multiply 8 and 4, carry the 3, do 16 plus
Yeah, that's
3.
what I-
I don't know what you just
That's-
said first.
That's what I'm saying. So I would prefer that you understand why the standard is working. Like you're doing 8 times 20. and then 8 times 4 and adding those.
I do that in my.
That's what the rectangle method is doing in an organized way. Lattice, I have no idea what it's doing. I think it's the same, organized different. So I don't know.
I was just thinking while we were doing this, who thinks up integrals first, and then who thinks up to replace it with you? Yeah, and like what?
Probably-
Who made that out? I was wondering, why do we even know if that's not good up or something?
That's good.
That's the thing, I was like, what if we use that?
What is math?
Well, that comes into like business application when you're talking about like, you ever heard of the point of diminishing returns? Never heard that phrase? Where like if you stay up all night studying, there comes a point where you're not getting as much out of it and you're better off just going to sleep. Like you reach a point where what you're doing is not worth doing what you're doing. And that is what an inflection point is. Like the point at which it's no longer worth it.
Yeah.
And when you get into business application, that's the point when you get into like profits. It's no longer worth manufacturing this many things because you're gonna start losing money, things like that.
But isn't math like so?
Huh?
I'm a line in this stuff. I'm literally just looking at the
I don't know why you took the class. I didn't schedule.
I have to take calculus, it's like one of like the
Okay, but is it
general
math?
classes that I have to take in college or whatever.
You could have taken AP stats.
But I think stats and calc.
Isn't math like super old? So who came up with this?
Yeah. This is the first.
Well, was
Like, how did they come up with that?
Was it invented or discovered?
Well, I feel like it was, I mean, like, both. Kind of. I feel like they could have found different ways to do
How do they
something.
know?
They found, like, they invented a way, but there could be like multiple ways that you find something. Like, I don't think that they, like, who invented
Yeah.
stuff?
Doesn't make, nothing really makes sense.
Like,
Should probably stop the record. Forgot.